Mine are all.
I don't know, man. Alright, so we're switching over to means. We're basically going to do the same four things we just did. One interval, two intervals, one test, two tests. Same thing we did, except we're working with the average of something instead of the proportion of something. Yeah, so just start doing it. So it's like not live. It's live. There we go. Okay, so it's been a while since we've done stuff with means, so let me remind you of the conditions. So for shape, it's approximately normal. For means, if, and then there's actually three things that can happen. We only have done two of them so far. The third one's pretty annoying, that's why I kind of avoided it. But, we had a sample size cutoff, that if you have a sample size bigger than this number, then you can say that your sampling distribution is approximately normal. 30. So if you're taking n is greater than or equal to 30, you're good. If it doesn't say n is greater than normal, remember the other condition that we can apply. What did I just say? Is that what I said? Yeah, I was thinking like both things at once. If it doesn't say n is greater than 30, what other condition can we use to verify that it'll be approximately normal? So 10 successes, 10 failures is, think about that. You get like 30 out of 50. So like 30 failures, 30 successes, 20 failures. But 30 out of 50 is a percentage, right? A proportion, not a mean. So it's different. You said central limit there. That's this one. If it tells you the population's normal, then the third one, if either one of those happen, so they give you a small sample size and they don't tell you the population is normal, you have to make a sketch. So I would do a dot plot that shows approximately normal. That's just annoying because it's like this extra side quest you have to do before you get back to the real problem. We will have to do that. It's not super often, but it does come up. Alright, the center, the mean of your sampling distribution, is the same as the mean of the population as long as what's true. Same thing for proportions. How do we know the center was the center? Right. So these two are the same with means and proportions. It's this one that changes. So for the spread, standard deviation is going to be the population standard deviation divided by the square root of n. So we've seen that before, we've talked about it before, but let's just review a little. So as n goes up, what happens to the standard deviation of the sampling distribution? It goes down. So if I have a bigger number down here, I'm dividing the standard deviation into smaller and smaller parts, so my standard deviation will go down. That's true as long as the dependence, which is the n is less than or equal to 0.1 times the population. all true, then we can say the distribution of x bar is approximately normal with a mean of mu and a standard deviation of population standard deviation divided by the square root. So our confidence interval becomes x bar plus or minus z star. That's our critical value, right? Times standard deviation, which is this one. Yes. There's like an amazing question that someone asked that we blown away. I'm curious to see. I didn't mean to put pressure on you, I'm sorry. Okay.
I actually think it's a super question. So about the shape, I know that you kind of already explained it, but I didn't understand your explanation. About why we can't use the 10 successes, 10 failures thing.
So if I tell you the average height in here is 70 inches,
yeah.
Tell me what 10 successes and 10 failures would, how that would apply.
Oh, because this is for means, and that's why it's different?
Yes.
Okay.
So it doesn't apply, right? Because you don't have success and failure, you just have like a number.
Okay.
Okay. There is an amazing question though that I'm waiting for someone to ask. What do you mean? It's a long one. Where am I given the standard deviation? Because the spread of the sampling distribution is smaller than the actual. This is like the population standard deviation. So I know like the standard deviation of all of your heights is 3 inches. Well, then I take a sample of like 5 and I write down that average. And I take another sample of 5 and I write down that average. And I start averaging the averages. And when I average the averages, it's tighter because you can't get the outliers as much. So that's why this happens. But you're close. Let's see if we can figure this out now. What is weird about this? So I'm telling you to estimate the population mean. So I have a sample of 30 of you. I know your average height is whatever, 70 inches. I want to estimate the population mean, right? Because I only have a sample. I don't know the big picture. So what I'm telling you is to do that. Take the standard deviation of the population and divide it by the square root of like 30. It's 30. What is weird about that? Well, that's fine. Not really. I mean, kind of. Let me just like try to say it again. So, we're trying to estimate the average height of students at this school. Right? What's up? Did you scale it? Okay. I want to estimate the population, the average height of every student in the whole school. My attempt to do so is to take the average of the 25 or 30 of you, let's say 30 because so we can meet the condition. And to do that, what I'm telling you to do is take the standard deviation of the population and divide it by the square root of 30. What's weird about that? What? Another way to phrase that would be, if I know the standard deviation of the population, I have to know the mean of the population. Like the formula for standard deviation is how far you are away from the mean, right? So if I'm asking you to estimate the population height, but in order to do that, we're going to use the population standard deviation, doesn't that mean I already know the average height of the population? Does that make sense? Let me try it again. We're getting there. Let's try to establish this issue first. So, what's the formula for standard deviation? You don't know the formula, but you have to know the mean. If I said find the standard deviation of the heights in this room, you would do your height minus the standard deviation, minus the average, and then work with that. So how far away you are from the average of standard deviation. So if I know the population standard deviation, the standard deviation of every student in the school size, I have to know the mean of the population. That's the only way I can get the population standard deviation. If I know the mean of the whole population. And what I'm saying is let's do this procedure that tries to estimate the mean of the population. But I just told you we already know. Isn't that weird? Are you not seeing the weirdness, or are you just like... Okay, that's fine. Do we see the weirdness? I'm getting to the point. Patience, Higgins. The point is, this is like hardly ever used. Like, I don't recall more than 5 questions I've ever seen in the AP test about this. So I'm showing you this, and then I'm going to go through like, okay, now we really don't know the population standard deviation. What do we do about that? So I'm going through this one. We're kind of learning the process. You kind of know the process already. But keep in mind that this one we're doing here, and we won't do this one ever again, is not really like a real world example, because I'm asking you to estimate a thing, but to estimate that thing, you have to use something you already know that you don't need to estimate anymore because you already know. It's like a weird circular code thing that would just never happen. Okay, so I'm going to go through it, and then I'm going to show you, okay, what happens if we don't know the population standard deviation, which we really don't. So we're going to go through and do one. We are going to do a confidence interval. Hold on, there's a good way to phrase this. I'm sorry. A Z confidence interval for means. So they kind of get around the issue of like knowing it when say suppose the standard deviation has been this. That's a tweak that they can make, I guess, to make it kind of work, but I still have no CDs on that. I'm trying to teach the process. So we're going to say the same thing we did before when we did Z's. So with means. So mu is going to equal true population proportion of, what are we looking at? The weights of the tomatoes. We're going to do a 99% confidence interval. So let's jot this down. 99% confidence interval. N equals 4. The mean is 110. Okay. Conditions. I'm going to try to squeeze these in here. So shape.
Why is that N less than
Oh, mean. True population mean. Sorry. We've written population proportion every day for like 3 weeks. What was your question then? Okay. N is 4. That's really small. It's not bigger than 30, so I can't use that. But how do I know the shape of my sample is going to be approximately normal? I don't have to sketch it, unfortunately. Yeah, it says the population is normal. So the shape of my sample is going to be approximately normal because the population is approximately normal. The center of my sampling distribution will be 110 since we used randomness. Random samples. And then the spread is going to be So you could say like standard deviation divided by the square root of n. You could put the numbers in and say, okay, that's 40 divided by the square root of 4. Because what's the condition here? Less than 10%. So we have to assume 4 is less than or equal to 0.1 times all the tomatoes. Alright, so now we go to the math. I'll catch you on the page, or are people still right? Still right. We good? How'd you get? Okay. So now the math part, we would say statistic plus or minus the critical value times the standard deviation. So x bar is our statistic because we're working with averages now, not proportions. Critical value z star. That's going to change. And then your standard deviation of your sample is whatever your population standard deviation was divided by the square root of your sample size. So our x bar was 110. Z star, it's at 99%. So how do we find z star? There's a norm of 1.99 divided by 2. Wait, what'd you say? Are you trying to guess? Are you trying to guess what he means? You're getting 2.576 ish. Okay. Alright, so the standard deviation is 40. And the sample size was 4. And then we're not going to do that. Go to your calculator. You could. I think it's a lot easier to use your calculator. So we are learning today, we're learning z interval and t interval. That's like the two things we're talking about. T interval is way more common. The z interval, like I said, is kind of weird. Using something that you pretend you don't know to find something that you pretend you know. But this is z interval. So we haven't used the z star, z interval. So we're going to go, did you guys on stats or data? Default to data? So go over to stats. We're going to do data today too, though. Go to stats and then put in everything. So our standard deviation was 40. Don't do 40 divided by the square root of 4 there, because it's going to do that part for you. Like if you divide by the square root of 4, it's going to divide by the square root of 4 again. That's a little excessive. Mean is 10. That is 4. 0.99. So I get that. It's pretty big interval. Are we getting that? We agree? Okay. So, 58.48 to 161.52. So then we would conclude it and say we are 99% confident that mu is between those two numbers, between 58.48 and 161.52. So the reason that it's so big, that interval, is because that was such a small sample size. The bigger the sample size, the narrower your window. Okay, so we just did so we did a z interval was talking about what I was trying to get to before. So when we constructed this, we assumed that we knew the true population. This, of course, is silly, because if we were trying to find an interval of plausible values, how could we possibly know the standard deviation, which we need? You get in the cyclical thing, where you're using something that you know to find something to try to predict the thing that you already know. So if we don't know the population standard deviation, which is the case like basically every time, if you knew it, there would be no reason to try to guess. If we don't know it, we use what's called a t distribution. You use this when you don't know the population standard deviation, which is basically all. So a t distribution has a little bit more uncertainty because you're estimating. You're just kind of hoping that your standard deviation from your sample applies to the bigger picture. You're not sure, so you got to give yourself a little bit of wiggle room. So the z distribution gets a little wider. You have like more uncertainty, so there's more margin of error. So it's still centered at 0. So I'm trying to describe this is a t distribution. This one is a t distribution. Other one, like your normal, your z. So see how this is more spread out because we're less certain about what the standard deviation is. It is still bell-shaped. Its spread is slightly greater than the standard deviation. And it has more area in the tails. The area under all of that still adds up to 1, like that, where it's all the same. And we're going to adjust the graph a little bit. Let's call this a t distribution with a sample size of 29. Let's say. Just make it up. The more data I get, like the larger sample size I have, the closer that this t distribution gets to the standard normal distribution. So this is if we knew everything. We don't. We don't know the population standard deviation, so we have to guess. So this is our first guess. Like that's a small sample size guess. If I got a bigger sample size, it would look a little more like this, where it's kind of in between. And so this would be, this one is a t distribution with like maybe a sample size of 100. And then if my sample size were 200, it would get a little bit closer to the normal. If it were 1,000, it would get a little bit closer. The more data you have, it eventually becomes just like a normal curve once you have enough data. All right, turn the page. Dang it, that's what I just did. Okay. So there's a unique density curve. The density curve is the curvy bell-shaped thingy. And it depends on what's called the degrees of freedom. And the degrees of freedom is what you need to know about it is the sample size minus 1. It's a thing that you'll get into more in college if you take like an advanced stats class. They only like touch on it here and make us use it. You gotta have to use it to do these problems, but they're never gonna ask you to explain it. So I'm not worried about going into it. This is exactly what I was just doing. So degrees of freedom is 4 is the slower one, like more spread out. Degrees of freedom is 30 would be a little bit steeper. 100 would be closer. And I want you to look at this bottom one. And we're not going to use the chart except for a second. How do you calculate t-star? So we got to do this like that. So it's not inverse norm anymore. It's normal and z go together. It's inverse t. And then we do the 1.9 divided by 2, or the 0.05 if some of you guys are doing it that way. But if you go to put that in your calculator, I'll show you where the inverse t button is. You go to your distributions. Inverse t is like the 4th one. So if I go to put 1.9 divided by 2 in closed parentheses, it's going to give me an error. Because the value of that t star changes depending on your sample size. So if you look at this chart over here, let's just focus on one. Let's say this. So this would be like a 90% value for the critical value. So look at what happens. First of all, the inverse norm of 1.9 divided by 2 is that. That's your z-star. This is what like the actual normal data. When we have degrees of freedom of 21, which would be a sample size of 22, the degrees of freedom is 1 less. If I find the t-star for that, it's 1.7, or 1.72, then it's 1.71. As my sample size keeps getting bigger, now it's 1.70, 1.68, 1.67. And then you can see as my sample size gets bigger, it gets closer and closer and closer to the actual value of normal curves. So the t-star is an estimate, so it's wider, but as we get more information, it gets closer and closer to normal. So to type it in correctly, you would have to tell the calculator, because it changes, right, depending on your sample size. You have to tell the calculator the degrees of freedom. N is 30, the degrees of freedom is 29. And you hopefully are getting 1.69 back. Yes, 1.699? Alright, let's do it on the next page. Find those. I really like that the calculator gives you an error. It kind of stops you from making potential mistakes. So that's what I got for that one. Remember, you go in second bars, where you get like the distribution. Then inverse t. We good there? You get the same thing? Yeah. The left, right, center thing? Oh, it's some other. So you put 1.96. Okay, so we're going to go back and do the same thing we did in the beginning, but now we're doing it with a t distribution instead of a z distribution. Because we're actually saying, yeah, we actually don't know the population standard deviation. Let's figure that out. Conditions these are all the same. Like we've done all that. Nothing changes here, so I'm not going to write the conditions again. Okay. So let's just jump to the problem. Well, this is a good summary. One sample t interval for means is going to be x bar plus or minus t star times the standard deviation divided by the square root. And then the z interval would be x bar plus or minus z star times the standard deviation of the square root. We use this if you don't know population standard deviation. They put S of X there, so you can, that's kind of interchangeable. That could be S of X. That means like the standard deviation of the sample. So you will very, very rarely use this. What? You got something to say, Gunnar? What do you got? I thought you could comment on it. No, not you. I thought Gunnar was. I was going to fight Gunnar. We'd like kind of finish the lesson first. Okay. So then,
Wait, go.
oh. Keep your calculators out because I'm going to show you something else. And this is an information packed. More stuff coming. What? The day of learning.
Alright, you good.
Are we good? Can I turn the page? Okay. Alright, so we're going to do this one. So if you want to take a second to read through it, we're going to like do the problem. Then there's something new I'm showing here too. A couple new things actually. So they're saying this article reports if you average 300 minutes a week of exercise, you won't get cancer. Definitely not.
I don't know that one.
I don't think that's the same. So I take a random sample of 10 U.S. adults on their exercise per week. I want to find out the 95% confidence interval for the true population mean of like all people. So this is a Z interval. No, sorry. Sorry. Is this a Z interval or a T interval? T. It's T because I don't know the standard deviation of the population. I can find the standard deviation of my sample. That's fine, but I don't know the population. So this is a T interval. For means. No. So that's why the calculator says T. So I just try to reinforce. So mu equals the true population over proportion. Population mean minutes per week of exercise. 300 minutes. What, 40, 45 minutes? Modern exercise. Yeah, so like walking. Not vigorous.
That's 5 hours. That's bigger.
Yeah, like sauntering around.
Yeah, like we're just going to class. Like I'm going to walk.
Okay. N equals 10. X bar equals, and the standard deviation equals, I don't know. They didn't give me those. They could have, but they're just being annoying. So I need to find those. But I'm not doing it by hand. I'm going to make my calculator do it. So we did this a long time ago with one variable stats. So you're going to go stat, edit, type those numbers into your L1. Then stat, and then edit. Remember, you can go up to the top and hit like clear, then enter. It'll clear out the whole column for you. Don't hit delete though. Delete deletes the entire column. And then I'm just typing in my data set. So once you get that in, hit stat again. We want to calculate, so go to calc, the one variable stats. And it'll tell me that the mean is 23.2. What do you work frequency?
Second. Just a second. I got it now. Yeah.
So that's on like the different kind of line. So it's frequency list.
Yeah, you just it'll automatically put L's on there, but you just have to clear it. Otherwise, it'll.
I'll try to use that too. Are we good though?
Yeah.
Okay. So I got that's the mean, that's the deviation. You guys agree? Point 8 for what? Then you type something in right.
Standard deviation is 1.87.
Yeah, this is right. I'm very confident. Take a second and look if you.
I'm not saying you're wrong. I don't know what's on the air. Bro, how else do you have to read?
And what's your mean?
I got
over
283.9
there?
now.
No, I got the 20 point something for the SS.
Are you sure you didn't look at the sigma? You want the S.
That's the one that I got.
Oh.
That was crazy.
Read me your numbers. No, like the numbers in your calculator.
I just got 284.
Check. Check. Yes. Yeah. Yeah.
I did the same thing, and I got stat. How 1 million stats.
You get second stat where you get.
Well, you probably have to take it or something.
Do you have any other things? Okay. So if you're getting different if you're sure you typed them in, you're getting different numbers. Where it says frequency list, which not everyone's calculated that, but if it says frequency list, clear it out. Clear it out. Instead of putting L1. And then you should get the 283.2.
Yeah.
That's why. Okay.
I got
Since that. Yeah, just let it. Okay. Alright, we gotta get this list. Shape. Approximately normal. Because. And this is the annoying one. Is 10 big enough? It's not. And if you read through the problem, it does not say that the population is normal. So what you've got to do is sketch. This is not like a super detailed graph, a dot plot. So my lowest number is what? 243s. My biggest one's like 325. So I'm going to go by like 20s. 260. Do not overly detail this graph. It's very restful. And then just make a dot plot. So every point you see, put a dot approximately where that would be. So like 265 is here. 274 is about there. 281. 289. 304. I'll stop saying all my numbers. 275. 90. 25. 286. And then what you're going to say is approximately normal because dot plot shows no skew or outliers, or you could say because dot plot is approximately normal, or appears approximately normal. Which I think it does. You got like a couple things with tails, and as you get closer to the center, there's more and more things. Alright.
Theoretically, we're given a problem that was not
So theoretically, your LAP test, you get this problem. It doesn't say approximately normal. You don't have 30. And your dot plot, let's say it's just like it's just a really weird, like, not, then you would have to say, like, the conditions are not met. And what you would actually say is proceed with caution. But I've never seen that happen. So that would mean, like, the conditions aren't met. Go ahead and do it, but, like, be careful on the conclusions you draw. But it wouldn't happen. The only way it would happen would be on a multiple choice. Like, are the conditions met? Yes or no, and why? And then they can, like, just ask you that part instead of having you do the whole thing. I mean, but then you wouldn't know if it was. So I could give you 10 data points and say, is the population going to be, or is the sample going to be approximately normal? And the choice would be like, yes, because I have a sample size bigger than 30. That's wrong. Yes, because the population is normal. That's wrong. Yes, because the dot plot appears normal. That would be wrong. And then that could be wrong. And then part D could be like, no, because the dot plot does not appear. You know what I mean? Oh, you're saying if I can eyeball it? Yeah, that's okay. You trust your eyeballs. Okay. Yeah, like a multiple choice, you never have to like show it. If you do have to show it on a free response, it's always going to work out. Okay. So that's the shape. Center. The center of our sampling distribution is going to be 283.2 because random sample. Spread is going to be 22.04 divided by the square root of 10 because 10 is less than 0.1 of U.S. adults, or are more than 100 U.S. adults. Okay. So then I'm going to go statistic. My formula part statistic plus or minus critical value times standard deviation. So remember I'm doing it in words, in symbols, in numbers. So then in words, their statistic is X bar plus or minus what's my critical value in symbols. Because I don't know the population standard deviation. It's T star. If I knew the standard deviation population, it would be C star. And then your standard deviation is the standard deviation of your sample divided by the square root. And you plug in the numbers, so X bar is 110. T star I gotta find out. So remember that is inverse T 1.95 divided by 2, comma. Where is what coming from? 110 is the mean of the previous problem. I just remembered. That should be 283.2. When you do this over here, you're going to point at that 9 and say, hey, that's the degrees of freedom. And you can just put D in. Yep. That's too much for you. Yeah, just over the top. T star. So then find this. 1.95 divided by 2. Inverse T of 1.95 divided by 2. Common diagonal. So I get 2.26. You get that? 2.26? What's my standard deviation? 22.04 divided by the square root of 10. But now go to your we're not doing that. I ain't doing math. It's crazy. Go to your calculator and there's like another thing that comes up in this that is new. I'm telling you, information X. We are going to even beyond that. Is this a Z interval or a T interval? T interval. Why? Not because that's what we learned today. Why is it a T interval?
We don't know the standard.
Don't know the population standard deviation. It's T interval. You can do this two ways. So did yours pop up with that? Isn't that cool? So you never typed that in. Like it just grabbed it from your one variable stats. And it knows like, oh, that's what you're about to do. So put them in there. So that's one thing I wanted to show you. Yeah. Where it would grab it? If you put it in the L1, yeah. You never did that before, where you typed in all the data. We would just tell it, like, the mean is this, the mean is this. Oh, I know what you're talking about. Yeah, so sort of like that. Yeah. Okay. So go ahead and calculate. And 5. I'm going to show you stats now and data in a second. Go ahead and calculate. So that's what I got. $267.43 to $298.97. Two more things I want to talk about. I'm going to skip the conclusion because you're probably getting tired of listening to me. I don't blame you. This has been long. The question asked, do we believe that? So they said, is there enough evidence to support the fact that the average American gets 300 minutes a week of exercise, given that interval? No, why not? Because 300 is not it. Would there be enough to support like 275? Okay. Second thing I want to show you is go back and change. Let's go to your list again and edit it. And just put, I'm going to put like 2 more values at the bottom. Just try to change it. So I'm going to say like 300 and 400. So now go back to your test. So go to your T interval. Notice that, so is that still the mean standard deviation after I put in 2 numbers? It's not. So it only fills in there. That's the same mean standard deviation I had before, isn't it? So when I added those 2 numbers, it's not, it still says that equals 10, and now it's 12. So it only fills in if you do the one variable stats. But here's the cool thing: go to data, and you could just tell it like, I'm not gonna tell you the mean standard deviation. You figure it out. Data's in you. You do it. Your list is in your data's in L1. Frequency you want to be 1. I think you can probably clear it. 0.95, and it'll do the whole thing for you. So here's your new mean, here's your standard deviation, here's your interval. So you can tell your calculator, look in the list and just use those and you do everything. That was a lot. We'll review a lot of this on Monday. Questions I can answer at this point? Yeah. What do you mean? Did you see that I added 2 numbers?
Oh, no, I didn't.
Yeah, so I was trying to point out, like, are we good? Again, I know that was a lot. Good job paying attention for as much you did. We'll practice it more Monday.